Lake Mead may be set to be at its shallowest levels in recorded history.
The Bureau released its 2- and 5-year projections earlier this year, showing levels hovering at about 1,000 feet.
Lake Mead, once a great reservoir of hope in the American Southwest, has lately become a stage for some deeply unsettling developments. The water levels have been shrinking for years, a victim of chronic drought and overuse, yet something recently happened that seemed to arrive out of nowhere. A sudden odd motion, a flicker of activity, a shift that was not predicted, not explained, and not expected. It feels as though the lake is whispering a warning. The very ground around and beneath it may be shifting in ways that bring to life our worst fears: structural collapse, massive shifting of sediments, or a catastrophic breach. What just showed itself at Lake Mead is an alarm that something far more serious may be unfolding than mere drought. Before we start, smash the like and subscribe buttons for more updates. That flicker of motion, captured on remote sensors or observed by satellite imagery, didn't fit established models. Experts tracking water levels, sediment, seismic activity, and shoreline erosion noted anomalies, inconsistent readings, unexpected tilts of the shorelines, microfractures appearing in areas that had long been stable. Some of the shoreline that once had been solid and immovable showed signs of creeping movement. The bottom contours of the lake, mapped over decades, seemed to be subtly changing. A few sonar surveys revealed small landslides underwater. Debris shifted down slopes, and sediment layers that had once been settled now looked disturbed. The lake bed was acting in ways not anticipated. When something this ancient, massive, and impactful starts giving us surprises, it triggers a cascade of fears. Could it be the precursor to a catastrophic shift of the dam's foundation? Could the lake's bed destabilize so severely that it triggers subsidence along critical supports of the Hoover Dam or undermines outflow conduits? What if unseen erosion is hollowing out subterranean cavities right under the dam's base? These are not fanciful imaginings. These are exactly the kinds of failures one dreads when dealing with water, rock, and gravity. The more experts examine the data, the more they see hints that the ecosystem of Lake Mead is being reconfigured in real time. Geologists point to the possibility of slumping banks. Water retreat exposes formerly submerged slopes, drying cracks appear, and when water rebounds or heavy storms hit, those slopes may give way. Those landslides can plunge underwater, displacing enormous volumes of water, creating pressure waves, undermining structures, or even triggering further slope failure in adjacent zones. A small slip could trigger a chain reaction along the margins. Sediment that has been stable for millennia may not be so stable anymore in a changing hydrologic regime. Another unsettling piece is that measurements of subsurface pressure, piezometric readings, are showing odd variations. Areas of the lake bed that should be under stable compressive stress are showing transient fluctuations in pressure, as though groundwater is migrating in unpredictable ways. That suggests that somewhere beneath the lake, hidden channels or fissures may be shifting, or being carved anew, allowing water to move into places where it formerly could not. And that movement weakens rock or sediment integrity over time. When weak zones develop beneath crucial infrastructure, trouble tends to follow. The entire system of dams, spillways, intake tunnels, and power-generating conduits requires a foundation of rock and sediment stability. If that foundation starts to shift, even slightly, it can misalign tunnels, open cracks, permit seepage, or lead to more serious structural distress. The real terror is that all of this might be going on below the threshold of human detection until a major event occurs. The last thing anyone wants is for a dam's failure to seem to arrive without warning. The recent oddities at Lake Mead suggest we may have come closer to that line than most people realize. Climate change, human mismanagement of water, and chronic drought are the background stressors, but they do not fully explain sudden anomalies. These new signs suggest that the lake system is entering a new phase of dynamic response. Not just decline, but active reorganization. When the terrain changes, water responds. When water behaves unexpectedly, the terrain adjusts further, and as that feedback loops, randomness can morph into danger. For those living downstream in the Arizona, Nevada, California corridor, the implications are grave. Lake Mead is critical. It supplies water to millions, irrigates thousands of square miles of farmland, and regulates river flows downstream. If the reservoir suddenly becomes unstable, it could affect the reliability of water supply, disrupt power generation at Hoover Dam, and even risk downstream flooding if structural failure occurs. The interconnectedness of the system means weaknesses in Mead cascade through the Colorado River network. A collapse at Mead could stress upstream reservoirs, overwhelm channels, or lead to emergency water releases with implications far beyond the immediate vicinity. One particularly grim possibility is that the anomaly marks the first signs of a dead pool approach. That is, a stage where the reservoir's water drops so low that turbines can't operate, intake pipes can't draw water, and flows downstream collapse. While that scenario has been discussed for years as drought intensified, sudden structural instabilities introduce a more chaotic and less manageable risk path. Instead of a slow march toward dead pool, you might see a sudden cutoff or shifts in flow that render dam operations unstable or unsafe. Even if dam failure doesn't occur, when the lake's internal structure changes, it can compromise the safety margins engineered into the system. A dam is never built to survive a shifting foundation indefinitely. It has tolerances and safety margins, but slow creeping deformation erodes those margins. The recent weird activity is evidence those margins may already be under stress. If cracks form in concrete structures or joineries between structural units slip, repair becomes more complex and dangerous, especially underwater or with high pressure. The worrying thing is that this sort of movement is stealthy. Unlike a flood or storm, you don't see a dramatic event until it's too late. You get tiny shifts, microseismic signals, minuscule deformations, acoustic emissions deep in rock strata. Only with dense monitoring can you hope to catch them. The fact that anomalous data was noticed only now suggests either that monitoring wasn't dense enough, or that the changes have accelerated recently. Either is unsettling. It means we may be in a regime change, a new plateau of instability to which our old expectations don't apply. Often in lake systems under drought stress, the shoreline recedes, exposing previously submerged rock faces and sediment slopes. Those slopes might not have ever adjusted to dry air and thermal cycles. When they become exposed, cracks form, water percolates deeper, freeze-thaw in cooler seasons further expands faults, and overnight shifts happen. Thus, erosion that once acted slowly now accelerates. A slope that had held firm for centuries might collapse overnight, sending debris sliding into water, displacing masses, and exerting pressure on adjacent structures. The anomalies now being seen at Lake Mead align with that kind of process. Beyond structural fears, there is a broader environmental threat. If lakebed rearrangements rearrange sediment layers, they may release locked-up compounds, heavy metals, nutrients, or toxic materials that had been buried under stable strata. Resuspension of sediments could degrade water quality, accelerate algal blooms, or disrupt aquatic ecosystems in unpredictable ways. A sudden slug of sediment could smother fish habitat or alter thermal stratification. That, in turn, could reduce the viability of the reservoir for ecological purposes as a habitat and filtration basin. Human communities dependent on the water could receive sharp and unexpected shocks. If supply lines become unreliable or emergency restrictions kick in, farmers, cities, and power producers would scramble to adjust. The sudden instability of the water system would ripple across agriculture, power, municipal supply, and ecosystems. A collapse of confidence in the reservoir's stability could lead to severe water rationing, emergency repairs, and public panic. The potential for cascading consequences is exactly why this sort of anomaly is so alarming. What makes this all more ominous is the lack of precedent in recent memory. Lake Mead's long-term decline is known. Everyone watching water budgets, snowpack, and climate models saw that coming. But a reservoir of this scale suddenly showing signs of structural agitation is rare. Almost no analogous case exists in U.S. reservoirs, especially not one tied to a major dam that underpins so much of the water infrastructure of a region. The surprise in this situation is not whether something bad will happen, but when and where. It is possible that what's being observed is an advanced warning, a window before major failure. A properly calibrated monitoring network, coupled with rapid responses, might intervene. Engineers could shore up vulnerable slopes, reinforce tunnel linings, strengthen grouting and seepage controls, stabilize or buttress banks, or lower lake levels to reduce pressure while repairs happen. But that requires planning, funding, political will, and prompt recognition that the current anomalies are more than just artifacts. The big fear is that these signs signal the onset of a cascade. Small slips trigger bigger slips, which accelerate deformation, which in turn overwhelms design tolerances, and eventually lead to failure modes that cannot be contained. That is the worst sort of disaster in dam safety. Failure not through a single obvious cause like overtopping, but through creeping decline of foundational integrity. What intensifies the urgency is that this problem cannot wait decades to solve. The moment a critical joint gives out, a fissure opens wide, or a supporting buttress fails, the window to act shrinks dramatically. Once that happens, emergency moves are limited, dangerous, and potentially too late. Authorities would have to scramble to reduce water loads, evacuate downstream areas, shut down power generation, and perhaps accept damage worse than if the issue had been addressed earlier. When a reservoir shows odd behavior, people often fear a catastrophic collapse. But sometimes what happens first is less dramatic. Gradual degradation, slowly losing capacity, increased maintenance, more frequent repairs, reduced operation margins. The problem is, with something this big, gradual may be measured in years and still result in enormous downstream impact. Water shortages, infrastructure stress, loss of hydroelectric output, and shock to dependent systems may unfold in a compressed time frame. The recent oddities at Lake Mead suggest that we may already be moving into that hazardous terrain. Even if the dam itself holds, if parts of the lakebed collapse or shift, the geometry of inflows and outflows could change. That could alter water routing, create unmapped dead zones, change the direction and speed of currents, and affect sediment loading patterns. Intake pipes and cooling intakes could be compromised. Pump systems could clog, strain, or fail. Any reconfiguration of underwater topography in a reservoir this large carries systemic risk. The psychological effect of something like this cannot be ignored. Once people believe the lake might be unstable, trust erodes. Communities downstream might demand cuts, stricter monitoring, contingency plans, insurance loads and liabilities increase. Projects planned around the lake's stability get delayed or canceled. The economic ripple is felt in municipal budgets, water rights disputes, agriculture, recreation, tourism, and industry. The very uncertainty becomes part of the hazard. It's tempting to imagine that the odd activity is just noise, a sensor glitch, a minor landslide, or a benign pressure fluctuation. But extreme systems often surprise us when they shift into new regimes. Once water levels fall below key thresholds, feedbacks change. Erosion, sediment transport, and geologic stability no longer follow the old rules. Suddenly, minor stresses, and that's exactly when we've been seeing them at Lake Mead, can tip things over. The chance that what is happening now is not noise but signal is uncomfortably high. Given all this, the imperative becomes clear. Better, denser monitoring, urgent geotechnical investigation, contingency planning for worst-case structural and hydrologic scenarios, and readiness to act fast. Without robust, real-time sensing of deformation, seepage, sediment movement, and subsurface pressures, critical warning signs can be missed. And once a tipping point is reached, reversal may no longer be possible. Those studying the anomalies already speak of this as a potential harbinger, a turning point in the life of the reservoir. A new phase where decline is not smooth or predictable, but violent, uncertain, and rearranging. Whether the lake simply slides further toward unusability or lurches into partial collapse, the trajectory matters. This is no longer just a crisis of water scarcity, it is a crisis of stability. All around Lake Mead, the ground is changing, the water is restless, the sensors hum with anomalies, and what once appeared to be a slow decline may in fact be the opening act of something far more dramatic and dangerous. The biggest fear is not that the dam fails tomorrow, the biggest fear is that the foundation is already failing invisibly, inexorably, and advancing toward a moment when the only warning left will be the catastrophe itself. The new signs at Lake Mead deepen as scientists dive into remote sensing data from radar interferometry, LiDAR mapping, and high-resolution sonar scans. The shoreline that once held a consistent slope now reveals subtle contour warps, arcs of differential displacement, bulges outward or inward relative to expected lines, as though the earth beneath is flexing like a stressed membrane. These distortions, measured in mere centimeters, may seem trivial, But on the scale of millions of tons of water and rock, even a centimeter of movement at a critical location can cascade into structural stress. In certain long stretches, the shoreline tilt seems to fluctuate over seasonal cycles, but now those fluctuations show uncharacteristic amplitude, variations larger than hydrologic models predict, and sometimes lagging or leading expected water level changes. That suggests ground motion independent of water load, as though subterranean forces are at play. Detailed bathymetric profiles taken over time are showing warp lines, where zones of the lake bed are nudging upward or downward in relation to adjacent areas, forming gentle warps or sinks. In some sectors, there's evidence of subsidence in patches, local depressions forming like shallow bowls, and adjacent ridges of compensatory uplift. Those differential motions strain boundaries between sediment blocks. The joints separating blocks of sediment and rock can crack, open, or shift. Through those openings, water can infiltrate, altering pore pressure, reducing cohesion, and encouraging further sliding. Such internal rearrangement may propagate outward, amplifying stress waves across the lake bed. Another emerging factor is the migration of groundwater pathways under the basin. High-precision resistivity imaging and electromagnetic surveys detect newly forming zones of lower resistance, indicative of water-filled conduits or fractures. In areas that once were solid, insulating, and dry from the lake shore inward, pathways appear where water now seeps deeper, rerouting through previously dry rock or sediment. The creation of these new pathways changes the local hydrostatic regime. Pressure gradients shift, and the weight of water applies force on new planes of weakness. In highly fractured rock beneath the reservoir, such change is dangerous. Pre-existing fault lines can be reactivated, or new fractures propagate in response to altered stress fields. In places where slopes were formerly stable, tilting of just a few degrees has been registered, often not continuous, but episodic. Geologists interpret this as evidence of slow creep punctuated by microbreaks. A slope will give way slightly, stop, restabilize, then creep again. Over time, that stop-and-go creeping can produce fissures, scarp formation, or even block failures. Some zones towards steeper banks show fresh tension cracks in overlying ground, especially in zones just above the exposed lake edge. Those cracks run parallel to the shore, at first thin, but widening over time, a clear sign that the adjacent ground mass is beginning to detach from interior mass. If that detachment proceeds downhill, a slab could slide into the lake en masse. The displaced volume might be huge, sending a wave or pressure pulse toward dam structures, potentially destabilizing intakes or concrete faces submerged near the margins. Underwater, the remapped terrain reveals new slump scars, faint crescentic outlines where sediment and rock have already collapsed into the valley. These slumps appear farther from the margins than historically noted and may have occurred recently. Some slumps are paired with sediment fans as debris slides down slopes and accumulates. That suggests the lake bed is reorganizing under changing hydrologic and mechanical regimes. The development of multiple slump zones in different sectors raises the possibility that the system is entering a multi-sector phase of instability, not just an isolated event. In some instances, the slumped sediment blocks are detached from deeper layers, forming cantilevered overhangs at the edges of collapse, precarious masses perched and ready to fall. Acoustic backscatter surveys of sediment layers show zones of disturbance. Previously continuous strata now disrupted by minor offsets, gaps, or tilting. The layering itself is no longer uniform. Some layers appear warped, others show layering truncated or offset across faults. That is evidence of active subaqueous shearing. Microfissures allow water to penetrate between layers, reducing friction and cohesion, making sliding more likely. The sediment body is, in effect, fracturing internally, weakening its integrity even before any visible failure. In such an environment, a triggering event, rainfall, seismic tremor, even a sudden change in reservoir water level, could push a weakened zone over the edge. It is not just the geologic and hydrologic realms that are being alarmed. Interdisciplinary analysis points toward thermomechanical interactions. As water levels fall, solar heating penetrates newly exposed ground, warming nearshore rock and sediment, altering thermal gradients. Diurnal heating and cooling cycles cause expansion and contraction, progressively stressing fractures and joints. Those thermal stresses over repeated cycles may gradually widen cracks. In zones still submerged but near the fluctuating interface, unstable thermal gradients in pore water can drive convection, moving warmer water downward, weakening layers under the thermal front. Over time, the coupling of mechanical and thermal stresses may produce patterns of fatigue in the rock sediment matrix that did not exist before. Given a shifting baseline of lake levels, these thermomechanical effects amplify. Places that were safe under full reservoir may now be vulnerable. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on Lake Mead's strange new activity? Sign of something bigger coming? We want to hear from you. Thank you for watching and see you next time.